Hi there. This video is going to walk through how entropy changes as we increase temperature starting at 0 Kelvin, or absolute zero. First off, let's make some indicators for our main baseline temperatures. Those are going to be our freezing point, room temperature, and normal boiling point. So let's say our freezing point here at 273 Kelvin. So our temperature is going to be in Kelvin on our x-axis. And then let's say our room temperature, 298 Kelvin, and put our boiling at 373 Kelvin right there. So those are going to be our anchor points to start with. And then likewise on our y-axis for entropy, we have some anchor values given here. So we have our standard entropy values for our solid, liquid, and gas. Okay, so we'll just put those markers in there to start with. So we'll say that's about 41. We'll say we have 70 there, and we'll put 189 up there. Okay, so next up we can start putting in some of our points that we have listed here. Okay, so again, going back to our standard values for entropy here. Remember this this 0 or not, NAUGHT, symbol means those are our standard conditions, which are going to be 25 degrees Celsius or 298 Kelvin. Okay, so that brings us to this point on our plot. So we're just going to mark those standard conditions as anchor points. So for our solid, we know our standard entropy of our solid is 41 joules per Kelvin. So we'll put a dot there. And then we have a standard entropy for our liquid of 70. So we'll get a dot there. And then finally our gas is up at the 189. Okay, so we'll just stack all of those points up for the standard conditions of each phase, and then we will go from there. Okay, so all of the other points on this graph are going to fall under the non-standard conditions, and we have an equation that will help us to calculate the entropy under non-standard conditions. So remember here we are under constant pressure. Okay, so the equation that you're going to want to use is our S at a non-standard temperature is given by our standard entropy plus Cp natural log of T final over T initial. Okay, so for our ice slash water at 0 degrees, okay, we can calculate the entropy with this equation. So if we want S at 273, we will have our standard entropy for ice is 41 joules per Kelvin, okay, plus our heat capacity for ice, which is 38, and then plugging in our temperatures. So 273 is our final temperature, and then our initial temperature is always going to be that reference point for our standard conditions, so 298 Kelvin. Okay, so punch that into your calculator and you should get about 38 joules per Kelvin. Okay, so that means that we can make a little spot right here at about, it's going to be at about 38. Okay, so now the question remains, how does my entropy change from 0 to my melting point? And then what happens to that solid as we continue to heat it up to room temperature, okay, or beyond? So a couple of things here. So let's start with what happens between 273 and 298 to our solid. So here we're essentially heating solid water, heating our ice. It's remaining in the solid form on this line. Okay, so we could just essentially continue this calculation out where we change our reference temperature here, or sorry, our desired temperature here. Okay, so this is going to continue to have essentially a logarithmic kind of behavior. So we can just kind of connect that dot in a log shape. Okay, and that's going to be the pattern that we see for the rest of our phases, right? So we're going to do the same thing for our liquid, okay, where here we're going to have a logarithmic kind of shape as we change the temperature either hotter or colder for our liquid phase, and then same for the gas phase, okay? One thing that is unique about the solid phase, though, is that once you drop to low temperatures, okay, we actually have a little bit of a quantum effect that plays a role in the shape of this curve. So it's not purely logarithmic going down to 0 Kelvin. So we all know that the entropy of a substance at 0 Kelvin is 0. That's our third law. Okay, so we know we're going down to that 0 point there, right? What happens between here and our 0 degrees is we get a little bit of a curvature. Okay, so this is the only part that's going to be a little bit different, okay, is for that solid phase at low temperatures. Okay, so this little chunk right there is representing some curvature due to quantum effects. Okay, so that's all next semester 341 stuff. Okay, don't worry too much about it now, but that would be what we call our Debye region. Okay, where we have some interesting quantum effects with our low temperature heat capacities. Don't worry too much about that right now, but just know that there's a little bit of a wonky kind of curvature shape here, whereas everything else is going to follow that natural log kind of curvature based on our equation here. All right, so next up is our liquid water. So again, that is going to, we're going to move from our solid. Okay, we're going to melt at 0 degrees, and then we're going to change our phase, which will increase our entropy to some extent. We'll figure that out in a second. Okay, and then we're going to continue to heat the liquid. Okay, up until we hit 373. And I just saw that I accidentally erased my boiling point. Okay, so next step here is going to be to calculate the entropy associated with liquid water at 0 Kelvin. Okay, so we already did the solid phase at 0 Kelvin. Now we need to calculate the same thing, except we're going to do it for our liquid phase. Okay, so again, just to note here, so that's our solid. So we want the same thing for our liquid. Okay, so you maybe pause the video and take a second and see if you can do that calculation and figure out where on this point here we want to put our anchor point for liquid water at 0 degrees. Okay, So if you punch that into your calculator, you should get about 60, 63 or so joules per Kelvin for that. Okay, which actually matches up pretty well with our delta S of fusion that we were given for our solid liquid phase transition at 273 Kelvin. That was given to us to be about 22 joules per Kelvin. So off by maybe a few joules per Kelvin, but again, remember we're using some rounded values here for heat capacities and such, so we'll be a little bit off, but I think we'll call that close enough. So if we can approximate around 63 or so, say right here. Okay, so if we again heat our liquid water from 0 degrees from 273 Kelvin, we'll heat that all the way up to 373. We're going to keep that logarithmic behavior. Okay, so we'll just approximate that, say kind of that shape. Okay. All right, and then we have, again, we can just mark this. That would be our delta S of fusion. It's about 22 joules per Kelvin. And then here, this point is about 60 joules per Kelvin. Okay, so this part takes us through our heating of liquid water. We can also continue to cool water below 0 degrees. Okay, and that would be what we call our super cooled water. So we'll just do, again, not our normal kind of situation, so we'll make that a dotted line, but that would essentially be what we would deem our super cooled water. And if you've never seen super cooled water crystallize before, Google that on YouTube and watch that video, or try it out in your own freezer, see how you do. Okay, it's a really, really cool experiment. Okay, and we're going to go through the same process for our water vapor. Okay, so we're going to have, again, anchor point here at 298. Okay, we'll heat our water vapor, or we could even cool it. Okay, but again, our standard point for where we start to get vapor is obviously at our boiling point, normal boiling point of 373. So this is where we'll have our normal state of water vapor. Okay, so this time let's calculate the entropy for our vapor at 373. So let's see where we're going to anchor ourselves up here for the vapor phase. Okay, then we can connect the dots. So take a minute, pause the video, and see if you can finish that calculation and estimate where we will be over here for our 373 temperature. Okay, so if we plug in our numbers for the vapor, okay, don't forget your heat capacity changes depending on what phase you're in, so just be careful on that. Okay, so here we're calculating our entropy of vaporization at 373 Kelvin, so we should get a value of about 197 is what I got. Hopefully you have something close. Joules per Kelvin, so that's going to take us up over, so here's our 189. We're going to be up a little ways from that value, so again, just ballparking here. We'll put an anchor point right there. Okay, so again, whether we heat or cool from this point, okay, we're still going to be kind of making that logarithmic shape. Okay, So we'll just connect those points. So our main phase there is going to be vapor past our boiling point, and we can kind of continue to cool below our normal boiling point. Okay, this, when we draw these dotted lines, another way of referencing these would be to call these metastable states. Okay, so these are not going to be what we call thermodynamically stable states for our system. Okay, so these bold lines right here, right, are our normal kind of existence temperatures for these different phases, right, under normal atmospheric conditions. Okay, if we go beyond those, right, this would be kind of super warm or superheated ice. Okay, this is super cooled water. This would be, I guess we would call that super cooled vapor. Okay, these are not stable states. So any kind of disruption here would really kind of kick everything into the phase that it really wants to be under those conditions. So that's why when you have super cooled water, you can get it there, but any kind of little speck of dust or disruption to that system is going to essentially instigate that system to go into its natural state, which would be, or in this case, it would be ice. Okay. Okay, same here. If you condense this, right, this would easily condense to form liquid water at those temperatures. Okay, so let's finish putting in some of our other labels that we can identify here. So again, here we have some information over here about a delta S of vaporization at 373. So that would essentially be that difference, right? So phase change between our liquid phase and our gas phase, vapor phase. Okay, that's our delta S vaporization at that temperature. So that's going to be approximately 110 joules per Kelvin based on our data that we're given. Okay, so that is essentially what you would calculate using delta H of your transition over, oops, not delta T, but T of your transition. Okay, all right, so you get the same value there. Okay, and then we have, let's see here, this would be what we would call our delta S of vaporization under standard conditions. Okay, so we'll get that little zero, that naught up there. Okay, so that's going to be, if you do the calculations with the values that you get out, you should get something at about 120 joules per Kelvin for that. Okay, so you see that your delta S of vaporization is going to change depending on what temperature you're at, right? So we have our standard delta S of vaporization, so that value at 25 degrees or 298 Kelvin, okay? And we see we get a slightly different value. I did not draw these to scale, obviously, because this is actually a smaller value. As we increase our temperature, we see we get a different value for that vaporization phase change. Okay, so this is how we essentially put together this little map of how entropy changes with temperature. Okay, so we have our set of calculations that we can do. Okay, so remember, this is the equation that you use whenever you want to calculate an entropy at a non-standard state. Remember this little indicator here, that zero, that naught symbol, is for 25 degrees Celsius or 298 Kelvin. So anywhere away from that, you can use this equation to calculate your entropy, and that's what gives rise to these kind of log behaviors. Okay, so this is our log behavior from that term in our calculation. Okay, so I think we've got just about everything marked up on here of interest. Again, we could keep, if you want to, you can keep heating this liquid water. This would be our superheated water. Again, not a very stable state for us under normal conditions. This point right here, remember that is from our third law, right, where entropy of a pure substance at 0 Kelvin is 0. Okay. This is our quantum mechanical little curvature that we get. Again, that's a topic for next semester. But everything after that just follows that logarithmic curve. Okay, and we can get our various delta S's that you might be interested in at these various temperatures. And I hope that this was helpful in giving you some practice working with our non-standard states and thinking about these different entropies of vaporization or fusion and how they fit in to our overall picture. Okay, hope that was helpful. Thanks.